All right, today we're going to pull back the curtain on a really impressive piece of technology, the V-Engine's M9 lighting and shadow system. Now, this thing was built from the ground up with a single, incredibly ambitious goal to create a totally dynamic world where light behaves just like it does in real life.
So here's our game plan. We're going to start with the core philosophy, the big idea that drives this whole system. Then we'll break down exactly how a single frame gets built. We'll explore the high-end ultra path that uses ray tracing, and then see how it cleverly scales everything back for more common hardware. And to wrap it all up, we'll look at the physics that makes it all look so real, and of course, the performance numbers that prove this whole crazy idea actually works. This right here, this is the mantra of the M9 system. It's a foundational commitment to a world that is always alive, always changing. Light behaves like it should, dynamically. Nothing is faked, nothing is pre-calculated or baked in. It all happens live, every single frame, in real time. So let's start with that core principle, because the entire architecture is built on a really bold decision to completely throw out a technique that has dominated game development for decades: light maps. You see, most game engines bake their lighting into these static textures. And yeah, it's fast when you're running the game, but it's fundamentally frozen in time. If you want a door to open and spill light into a dark hallway, or have a real day and night cycle, well, traditional light maps just can't handle it. The V-Engine's no light maps rule means every single interaction with light is calculated live, which gives designers just total creative freedom. So how in the world does the engine calculate all this dynamic light in just a handful of milliseconds? Well, it all starts with a process called deferred rendering. And the very first step is to create this kind of artist's palette for the entire scene, which is called a GBuffer. Okay, the V-Engine's GBuffer layout you see here, it's incredibly deliberate. It uses 6 different render targets to store every piece of surface information for the scene. But the most important design choice is right there at the top, in RT0. Instead of just storing depth and trying to figure out the position later, it stores the explicit, high-precision 32-bit world position of every single pixel. Now, that might sound small, but that decision makes every later calculation simpler. And crucially, it avoids all the nasty precision errors you can get in huge open worlds. And that GBuffer, well, that's the secret sauce for efficiency. By splitting the geometry pass from the lighting pass, the engine can handle scenes with hundreds of dynamic lights without breaking a sweat. It does all the complex lighting math just once for every pixel you actually see on screen, using all that rich data from the GBuffer, instead of wasting time doing it over and over again for polygons you can't even see. Okay, now for the fun part. Let's see how this all comes together on the ultra path. This is how the M9 system really flexes its muscles on high-end hardware with dedicated ray tracing cores, like our target here, an RTX 3080 Ti. So before the GPU can trace a single ray, it needs a map of the world. And that's where the acceleration structure comes in. Think of it like a hyper-efficient 3D index for the entire scene. A bottom-level structure, or BLAS, is built for each individual object. Then, a single top-level structure, the TLAS, organizes all those individual objects. It's basically a table of contents, so when a light ray is fired, this structure tells it exactly where to go, which means it doesn't have to waste time checking every single triangle in the entire scene. Now, what's so clever here is how optimized this is. The engine doesn't just use one brute force method for all its ray tracing. No, it strategically uses 2 different Vulkan extensions. It's all about using the right tool for the job. For complex, physically accurate shadows, it uses the full-blown ray tracing pipeline. But for something a bit simpler, like ambient occlusion, it uses these lighter, super-efficient ray queries right inside a compute shader. Smart. But, of course, there's a catch. Tracing hundreds of rays for every pixel would give you a perfect image, but it would take forever to render. To stay in real time, the engine only traces maybe 1 to 4 rays per pixel. And while that's fast, it creates a noisy, speckled image that, well, needs a serious cleanup. So how does it get cleaned up? The M9 solution is this fast and really effective bilateral blur denoiser. It's a single compute pass that intelligently blurs all that noisy shadow data. But here's the key part. It uses the depth and normal information we stored back in our GBuffer to avoid blurring across the edges of objects, so it cleans up the noise while preserving all the important details in the final image. This is all fantastic for a high-end GPU, no doubt. But what about the millions and millions of machines out there that don't have dedicated ray tracing hardware? You know, laptops with integrated graphics. This gets to the engine's core challenge. How do you scale this everything dynamic all the time philosophy all the way down? And here's the answer. the intelligent fallback path. This is a whole suite of really clever rasterization techniques, all specifically designed to run efficiently on hardware just like an Intel UHD 750 integrated GPU. This isn't just one trick. It's a whole toolkit of proven methods all working together in concert. You've got Forward Plus, which uses the CPU to sort lights into screen tiles ahead of time, keeping the GPU's workload nice and light. Instead of ray tracing for shadows, it uses Cascaded Shadow Maps, 4 different maps that give you incredible detail up close while staying efficient far away. And finally, you have techniques like PCF filtering and SSAO to add that final layer of polish needed to get close to that high-end look. And here's the best part. This fallback system is adaptive. It's constantly watching its own performance. If the time it takes to render a frame starts to climb, it doesn't just start dropping frames and getting choppy. No, it gracefully scales back visual features in a very specific order, like reducing SSO samples or pulling in the shadow distance, all in the name of maintaining a stable target frame rate. So we have these 2 totally distinct rendering paths, right? Ray tracing on one hand and rasterization on the other. But how does the engine make sure that materials look consistently realistic on both? Well, the answer lies in the unifying physics that govern every single surface. It all comes down to this, the Cook-Torrance BRDF model. This is basically the rulebook, the physically based math that describes how light interacts with a material. The GGX term models how rough a surface is on a microscopic level. The Smith function figures out how those tiny bumps cast shadows on each other. And the Fresnel equation determines how reflections get stronger when you look at a surface from a sharp angle. It's an industry standard for a reason. It just works.
The engine fully embraces the industry standard metallic roughness workflow. And what this means for artists is huge. It gives them the power to create materials that behave exactly like their real-world counterparts, from brushed aluminum to rough concrete. And they can be confident that it's going to look correct under any lighting condition on any rendering path. And this also shows how the engine handles really complex light sources. For area lights, think about a big fluorescent panel or a glowing monitor screen. It uses a brilliant technique called linearly transformed cosines. By using a couple of pre-calculated lookup textures, it can basically solve the super complex lighting math perfectly, and the result is these beautifully soft area lights with absolutely zero noise. It's fantastic.
Okay, so finally, let's look at the payoff, the performance. We've talked philosophy, we've talked tech, but does this ambitious dual-path architecture actually hit its targets in the real world? Let's look at the numbers. On the high-end RTX 3080 Ti, running at 1440p, the entire lighting and shadow calculation, from the GBuffer pass all the way to the final denoised shadows, is done within a strict 8 millisecond budget. That is crucial because it leaves enough time for the rest of the engine to do its job and comfortably hit high frame rates like 60 FPS, where you only have 16.7 milliseconds for the entire frame. And then we have the other end of the spectrum. On that fallback path, running on an entry-level integrated Intel UHD 750, the system hits its target of a rock-solid 30 frames per second at 1080p. This really proves the incredible range and the scalability of this one single architecture. To have a single unified lighting pipeline that completely rejects static, big techniques and yet scales this gracefully from high-end real-time path tracing all the way down to integrated hardware, that is a massive engineering achievement. And it really leaves us with one final big question. Is this kind of flexible, fully dynamic approach the new standard for the future of real-time rendering?